Question 1, part A. We're looking at how sodium reacts with water. This is reaction A. Now you're told that the sodium floats on the surface, gets smaller and eventually disappears in a colourless solution. So I have to state 3 other observations. Sometimes what pupils will do is repeat one of the observations that's given in the question. So you've got to think of 3 further observations here. So one would be moves. Another one is gives out heat. And final one, fizzes. You could say bubbles, they're the same thing. A fourth option would be that it melts. Sodium gives out a lot of heat, and the metal would actually melt into a ball. So you could say that as well. Part 2, reaction B, a half equation for a potassium atom becoming a potassium ion. Now half equations always contain E minus. So potassium atom is obviously K, and it goes to a potassium ion. Well, potassium has 1 electron in the outer shell. It will lose that 1 electron, and if it loses a negative electron, it will become positively charged. And then you've got to show that the electron is also produced. So that's the half equation. So there's a mark then for the K and the K plus, and there's a mark then for putting the E minus on the right hand side. You are also allowed to put K minus E minus goes to give K plus. But it's generally written the way I have it here. Okay, part 3. The balanced assembly equation for reaction C is as follows. Don't forget, when you're putting the halogens on their own, you always need a 2 because they're diatomic. So it's Cl2Br2, not just Cl and Br on their own. Now the colour change when chlorine gas is bubbled into a solution of sodium bromide. Well, sodium bromide solution is colourless. And you should remember that all of the compounds of group 1 and 2 elements form white solids and colourless solutions. Doesn't matter what they are. There's sodium chloride, magnesium nitrate, calcium nitrate, etc. So they're all colourless. And when chlorine reacts with sodium bromide, it displaces the bromine. Chlorine is more reactive than bromine. And when bromine is formed in solution, it's orange. And then part 5, we have to do another half equation. That's where we have to include the E minus of a bromine molecule becoming bromide ions. Well, a bromine molecule is Br2, it's diatomic. Bromide ions, Br minus. But look, it's Br2. So if you imagine the molecule looks something like that, it's made up of 2 atoms covalently bonded together. They split apart, and so you form 2 bromide ions. Now the bromine itself on the left is neutral overall, and on the right hand side you see that you've got a bromide ion which is negatively charged, and you've got 2 of those, 1, 2. So they're negatively charged. So that means that the bromine molecule must have gained 2 electrons. So that's our answer. Okay, on to the next question. Now, mass spectrometry is not on the specification any longer, but you should still be able to answer most of these questions. So how many isotopes of the element are present? Well, that's just based on the number of peaks. You can see there are 3 peaks formed. So the answer is 3. The isotope with the greatest relative abundance, well, that's going to be the highest peak. So that's 88. The identity of group 2 element using your data leaflet, well, you just go to your data leaflet, and if you look at the question, you're told that it's a group 2 element. You just find a group 2 element that has a mass number of 88, and you see that it is strontium. Now it just says suggest the identity, so you could also just do SR. You're not told to give the symbol or the word, so either is fine. Now part 4 is not one that you have to do, so we're going to leave it out. And question 2. So here we've got some calcium carbonate with an acid. So that'll give us salt plus water plus carbon dioxide. And we have to give observations when the calcium carbonate reacts. Well, carbon dioxide gas is given off, and any time a gas is given off in a liquid, you're going to see fizzing. Fizzing or bubbles. The solid will disappear. So in this case, it's an antacid tablet. So the solid disappears or the tablet disappears. Do not just write disappears on its own. That's important. And do not say that it dissolves. It doesn't dissolve. It actually reacts. So you cannot get the tablet back again. So it has to be just, that the tablet disappears. A colourless solution forms, because we're going to get calcium chloride. And calcium is a group 2 element. And remember, groups 1 and group 2, when they form compounds, the compounds are white solids, and the solutions of the compounds are colourless. So you could get a colourless solution. Another one you could put in is heat given out. Okay, so 3 out of those 4. The balanced symbol equation then, I'll just write it in now. The formula of aluminium hydroxide for part B. Aluminium has a valency of 3. I swap it and put it after the OH. And on the back of your data leaflet, you will see that hydroxide is OH minus. This minus tells it has a valency of 1. We swap it over. I don't need to put in the 1. Now, the hydroxide is made up of 2 different elements. So we've got to put brackets around it, because what we're trying to say is that there are 3 hydroxides to every 1 aluminium ion. The colour of aluminium hydroxide, now this here is a solid. We're told the antacid tablets contain aluminium hydroxide. It's going to be in solid form, and it's going to be white. I've said already that compounds of groups 1 and 2 are white solids, and the same also applies to the metals in group 3. They will also be white. Part 3, then we're going to have to do a chemical analysis or qualitative test to identify aluminium ions. Well, we could use sodium hydroxide solution. And again, it's important to put in the word solution. And that will give us a white precipitate. I'm just going to put in PPT, or you could say solid. And precipitate just means a solid that forms in a liquid during a reaction. Now, aluminium ions are not the only ions that produce a white precipitate with sodium hydroxide solution. Zinc and magnesium will also do that. So what we can then do is add excess sodium hydroxide solution, and the precipitate will dissolve. Now the question has a final sentence. Comment on the validity of the test. Now, aluminium ions are not the only ions to give a white precipitate. We've already said that. But the precipitate is not the only one that dissolves when the hydroxide solution is added in excess, because zinc ions will give the same result. So the test doesn't prove that the solution contains aluminium ions. It's possible, but it could also contain zinc ions. So it's not a valid test. It doesn't prove it's aluminium ions. Now you might think, well, could we use ammonia solution? Well, you could give the answer based on ammonia. So the first one would be add ammonia solution. You'll also get a white precipitate. You then add the ammonia solution in excess, but this time the precipitate does not dissolve. Now the issue with ammonia solution is that magnesium ions will produce the same result. So when a sodium hydroxide solution, zinc ions give the same result as aluminium. But when ammonia solution is used, magnesium ions produce the same result. So you can answer this question using ammonia solution instead of the sodium hydroxide solution. The flame colours, so sodium ion is going to be yellow or orange. The brick red substance is calcium ions, so we write Ca2+. Don't worry about the barium ions. It is no longer on the specification. It actually is a green colour. Here's another qualitative test we have to do to identify metal ions. This time it's iron 2. So we can see iron 2, that's Fe2+. And we've got to include these points. So let's see, we've got solid iron supplement, and that's important because the solid sample has to be dissolved in water before we carry out these tests. So the first thing you do is dissolve in water, or make a solution of the sample, and then add sodium hydroxide solution. And when it's iron 2, there will be a precipitate formed, and it's a green precipitate. Now the iron 2 ions are the only ions that produce that result. So I don't need to say about adding excess. And you could also use ammonia solution. Ammonia solution will produce the same result, a green precipitate. So we've identified the iron 2. Now we've got to identify the sulfate ions. And for the sulfate ions, we use barium chloride solution. And again, you should have the word solution in there. And when barium chloride solution is added to a solution containing a sulfate, a white precipitate forms. Now the final bullet point here is that we have to write ionic equations for the sulfate test, and the second bullet point, an ionic equation for the iron 2 test. So if we go back up now and complete this one, so iron 2 is Fe2+, and it reacts with the hydroxide part of sodium hydroxide. And when these come together, you can see that the iron 2 is a valency of 2 and the hydroxide is a valency of 1. So you swap those over, it's going to be Fe brackets OH brackets 2. So the iron 2 hydroxide is the green precipitate. We need to balance it by putting a 2 in front of the OH minus. And then the ionic equation for the formation of the white precipitate. Well, the white precipitate is barium sulfate. And the barium ions are what react with the sulfate ions. And both of these are soluble to start with, but when they come together and when they react together, it forms insoluble barium sulfate. An alloy, you remember, it contains the metal ions or atoms. So I've arranged them like so. And that's to represent a typical metal, but in an alloy, there are additional elements present. So if there is just one more present, one more type of element, so let's just represent it with this small black circle. What it does is that it prevents the layers of the ions from sliding over each other. So if you imagine trying to push it here, then this other element prevents the layer, and likewise this one prevents that layer from sliding over the other layers. And so that increases the strength of the alloy. So in terms of the definition then, an alloy is a mixture of elements, at least one of which is a metal. So there has to be a metal present. There can be two metals, can be a metal and a non-metal, but say at least one of the elements has to be a metal. So just make sure you don't say it's a mixture of metals. You'd only get 1 mark for that. On to part 2 then. Graphite is a giant covalent structure. So the bonding in it is covalent. It's not giant covalent. And the type of structure then is giant covalent. Iron is a metallic substance, so the metallic bonding is going to be present. And the structure, we can just say metallic. You can say metallic lattice. Now in this question, we're comparing the bonding and the structure of graphite and iron. So if I draw the structure of graphite, first of all, just to remind you of what it's like, you know, there are these hexagonal layers, like so. I'll just draw a couple of hexagons and then I'll do another layer underneath. And there are carbon atoms here, etc. So these are carbon atoms. And then the lines represent covalent bonds. And you remember that there are then van der Waals forces between, I'll just do VDW. So these forces exist between the layers. Iron is a metal, so it is going to have metallic bonding. And the diagram we use for metallic bonding is typically this. So you've got your positive ions, and then you've got your delocalized electrons. So now we need to transfer that information into the question. Okay, so these are the main points that you should have in your answer. And you need at least 7 of the points in order to get the full 6 marks. So if you've got between 7 and 9 of these points, then you just get 6 marks. On to B part 1. The bonding in silicon dioxide. Well, silicon, if you think of the periodic table, like so, and then you've got your zigzag line. Silicon is in the same group as carbon. So you've got carbon here and then silicon. Now carbon forms diamond and graphite. Those are giant covalent structures. So silicon is going to have the same type of bonding. That's covalent. Calcium oxide, well, calcium is over here in group 2, and then you've got oxygen over here in group 6. So you've got a metal and a non-metal. It's going to be ionic. Next, we have to draw a dot and cross diagram to show the bonding in sodium oxide. So again, we've got a metal, sodium, oxygen, which forms the oxide, which is a non-metal, so that tells us it's an ionic bond. So again, I'll just draw what you should have, and remember you need to show the atoms at the start, the ions at the end, and the charges on the ions. See, part 1 is about iron 2 oxide. Well, the 2 next to the iron tells us that the iron has a valency of 2. It is an iron 2 ion. So that means it's going to be Fe2 plus. Now the number of protons is equal to the atomic number. So you just go to the periodic table and look up the atomic number of iron, and you see it's 26. Now the number of neutrons are determined by subtracting the atomic number, or the number of protons, from the mass number. So that's going to be 30. The electrons, now in an atom, the number of electrons equals the number of protons. But this is not an atom, it's Fe2 plus. The 2 plus tells us that it must have lost 2 electrons. So if it had 26 electrons in the atom, it loses 2 to become Fe2 plus. The ion has 24 electrons. And then part 2, what is an ion? Well, an ion is just a charged particle. It's like a charged atom, and it forms when an atom gains or loses electrons. For part D now, we have to draw a dot and cross diagram to represent carbon dioxide. You should remember that there are 2 simple covalent molecules that contain double covalent bonds. One is oxygen and one is carbon dioxide. So both of these are simple covalent molecules, just made up of a group of atoms. These can exist then as individual molecules. So I'm going to draw the outer shell for carbon, and we only draw outer shell electrons when representing covalent bonds. So that's going to be the carbon, and I'm going to show then 2 oxygens. Now, carbon has 4 electrons in its outer shell. Oxygen is 6 in its outer shell. So that's going to bond there and there. Remember, a covalent bond is the sharing of a pair of electrons. So an electron from the oxygen has to pair up with an electron from the carbon. So we've already used up 2 of the 6 electrons in the outer shell of oxygen. 1, 2, 3, 4, 5, 6. And then do the same thing on the other oxygen. It's going to be 1, 2, 3, 4, 5, 6. Number 4, I've already written in the definition of solubility. So go and think of a container containing 100 grams of water, and we add the solid until no more can dissolve at a particular temperature. And when no more dissolves, we say the solution is saturated. So it will reach a stage when it's saturated that when we try to add some more solid, the solid will stay undissolved. And putting in the final point is important because generally for solids, as you increase the temperature, the solubility increases. So you must always specify what temperature you're talking about when dealing with solubility. Okay, which substance is most soluble? 10 degrees C. Well, this is 10 degrees C. And if we read up, we see that D is the most soluble. The y-axis is the solubility in grams of solid per 100 grams of water. It's just D. Part 2 then. what temperature do A and D have the same solubility? Well, the lines are going to cross. So this one is A and D, so just be careful that you're choosing the right lines. And that's where they cross. And that's at about 56 degrees C. Put in units. Again, generally you're allowed plus or minus 1. And for part 3, what temperature? 3 grams of substance C saturate 10 grams of water. Now, solubility curves always are done in grams per 100 grams of water. You can see that. So what you've got to do here for part 3 is work out the mass that would saturate 100 grams of water. So you've got 3 grams will saturate 10 grams of water. Well, at the moment that's no use to us because the graph, as I said, on the y-axis it's grams per 100 grams. Well, we can easily convert 10 grams of water to 100 grams of water by multiplying by 10. That means we have to do the same thing to the mass. Multiply that by 10. So look, now we've got it in the units that are present on the graph. We've got 30 grams per 100 grams of water. So now you can go up to the graph, and this is for substance C. Go to 30 grams and just read across, and you can see there it has a temperature of 70 degrees C. That's your answer. Okay, for this question, again you see that the mass of the water is not 100. So what you've got to do is convert each of these so that it is 100 grams of water. And then you've got to change the mass of substance as well. And then you can use the graph that's on the right hand side. Remember, these lines that are shown on the graph are really lines of saturation. They tell us the maximum mass of solid that can dissolve. So for example, if I take this one here, this is C. At 70 degrees Celsius, 30 grams can dissolve in 100 grams of water. So this line tells us the maximum mass, or what mass of solid is required to saturate the 100 grams of water. So what I'm going to do, I go through each of these. So A, we've got 10 grams of water. So I'm going to multiply that by 10, because then that will convert it to 100 grams of water, and then I need to multiply this, the mass, by 10. So that's 50. So then what I would do is I would go to 70 degrees C and find the solubility of A at 70 degrees C. So I'll just go up, and it's there, which is, if I can just see it, it's about 47, I think. It's around 47 grams per 100 grams of water. So what we're saying is, for A, at 70 degrees C, it's possible to dissolve 47 grams of the solid. If you go above 47 grams, no more can dissolve. Now, the question states that we have 50 grams. You can see that. And remember, A at 70 degrees C can only dissolve 47 grams of solid. Well, obviously 50 is greater than 47, so A is going to be saturated. So mixture 1 is definitely saturated. And you do that then for all of the others. So let's try number 2, or mixture 2. Okay, I'm going to convert that to 100 grams of water. I divide that by 5. So that means I would divide this by 5 as well. That would be 36. So at 40 degrees C, this is substance B. So I need to go up, and I can see that substance B is there. That's on 40. So substance B at 40 degrees C can dissolve 40 grams of the solid. Now in the question, we're told that there are 36 grams. Well, that's not 40. So this mixture, this water, can actually hold 4 more grams of substance B. So mixture 2 is not saturated. Okay, let's try and have a look at number 3. And I'm going to multiply that by 4 to bring it up to 100 grams of water. That means I need to multiply this by 4. It's at 10 degrees C. Okay, so then I go to the graph and look, okay, if it's at 10 degrees C, what mass of substance C can dissolve? So I go up, this is it, and I can see that 5 grams of solid will dissolve. That's the maximum that can dissolve. And go back to the question. Well, if I have 8 grams, that's more. Therefore, mixture 3 is also saturated. And then finally, we'll have a look at D. At 250, I need to convert that to 100. What you can do here is just divide by 250 and multiply by 100. And therefore you do the same here. Just divide by 250 and multiply by 100. So that's 32. It's at 30 degrees C. So I'm going to go to 30 degrees C and then find D, which is this line here. You can see just up there. And that's at, it's 47. So at 30 degrees C, 47 grams of D can dissolve in 100 grams of water. Well, in the question, we've only got 32 grams. So that's less than what the water can hold. So D is not, or mixture 4 is not saturated. So the answers are just 1 and 3. On to number 5. When a substance breaks down when heated, that's known as thermal decomposition. And if you look at the equation itself, you can see that there's one reactant and then it goes into several products. So when you see something like that, that's a decomposition reaction. Okay, on to number 2 then, reacting mass 1. Well, we've got, I'll write down, first of all, the main parts. So we've got magnesium nitrate, because we've been given the mass of it. And it's going into nitrogen dioxide. That's the other part, or the other substance that we're interested in. And you can see from the original equation up at the top, it's a 2 to 4 ratio, so 1 to 2. The first thing I do is work out the number of moles of magnesium nitrate. So that's going to be 4.44 divided by the RFM of magnesium nitrate, and that is 148. Remember, you do not use this 2 to work out the RFM. That's just to work out the ratio of moles. That equals 0.03. And we can see that it is a 1 to 2 ratio. So that means we'll get 0.06 moles of nitrogen dioxide. We can now convert that to a mass. Multiply 0.06 by the RFM of NO2, and it is 46. And that gives an answer of 2.76 grams. And for part B, we're working out the degree of hydration, or the moles of water of crystallization. And the container used is a crucible. So just to familiarise you or remind you of what the apparatus would look like, we'll have our Bunsen burner sitting on the or underneath the tripod. We don't use a wire gauze this time because we're going to use a pipe clay triangle, and this is our crucible. And then the magnesium chloride will be in there, the hydrated magnesium chloride. Again, if you're ever asked to draw a diagram, you make sure you label it. So what we're trying to do is work out the ratio of the anhydrous salt to the water. So the moles of the anhydrous salt to the moles of the water. Okay, part 1, the mass of water that's lost. And if you look at the results, here we've got the crucible and the hydrated magnesium chloride. So that contains water of crystallization. And this result is the crucible and the anhydrous salt. So it's now minus the water. So we're going to use these two calculations, or these two values, to calculate the mass of water that was lost. So the answer is 1.08. And to work out the moles, we just divide the mass by the RFM of water, and that equals 0.06. Now we want the mass of the anhydrous magnesium chloride. So here we have the crucible and the anhydrous magnesium chloride, and up here is the mass of the crucible. So if we subtract the mass of the crucible from the crucible and anhydrous magnesium chloride, that will give us the mass of anhydrous magnesium chloride. So it's going to be 14.82 minus 13.87, which is 0.95. We can work out the moles then by dividing 0.95 by the RFM of magnesium chloride, and that is 95. That equals 0.01. Now we've got the ratio of magnesium chloride to water. We divide through by the smallest one, which is 0.01, and you can see that it's a 1 to 6. So N equals 6. And for this one, for part C, again, I'm going to pick out the two substances that I'm interested in. I'm told I've got 0.475 tons of magnesium chloride, and I want to calculate the mass of hydrochloric acid that's required. So these are the two substances I'm interested in. So I've got to start with the magnesium chloride, because that's what I want to produce. I want to produce 0.475 tons. Now I need to turn that into grams, because when you're working out moles, it's always the mass in grams that you use. To turn tons into grams, you multiply by 1,000,000, 1 times 10 to the power of 6. So that's going to be 475,000 grams. Divide that by the RFM of magnesium chloride, and that equals 5,000. That's 5,000 moles. Okay, we can see that it's a 1:2 ratio. So that means that we need 10,000 moles of hydrochloric acid. Now we need to convert the moles to a mass. The mass of HCl is going to be 10,000 times 36.5. That gives an answer of 365,000 grams. Now the answer is in kilograms. So to convert grams to kilograms, we divide by 1,000. 365 is the answer.